Hi, what you're about to see is one of a series of short films from Tier 3 Solutions in which we outline ideas, principles or techniques which are bread and butter to us but may not be so familiar to everyone. We'll take the opportunity to answer some frequently asked questions too. The films should be a bit like the grey boxes you sometimes find at the side of magazine or journal articles that explain some of the background to a thing without interrupting the flow. If there's a specific topic or question you'd like to jump to, you may be able to find it in the timeline across the bottom of the frame.
Plant protection products are invaluable to ensure a reliable supply of safe, affordable food. But we need to consider animals that may be exposed to those products in their environment. The European Food Safety Agency requires that we carry out appropriate studies to support detailed assessments of the risk to wildlife. Tier 3 is involved in carrying out many such studies. If EU member states' regulators are satisfied that, among many other factors, the risk to wildlife species populations is acceptable, a product can be granted registration and may be sold and used. Common voles occur throughout most of Central Europe. Where they do not occur, there are populations of similar species, occupying the same ecological niche, such as the field vole in the British Isles and in Scandinavia. Their natural habitat is open grassland. They dig burrows in which they store food, raise young and shelter from predators. They tend to make runs through the thatch layer of established grassland, enabling them to move around easily and quickly and avoid exposure to predators. Voles also occur in arable crops, but these are usually harvested and cultivated or ploughed each year, destroying runs and burrows and killing many voles. This means that voles must recolonise arable crops anew each year. Because of this, populations in crops may be absent or only occur late in each year. Grassland and arable crops have very similar structure and growing pattern all across the range of the common vole, and thus across the whole European central zone. Grassland represents a worst-case scenario for small grazing mammals because the grass itself forms their diet, and because they're so numerous there. If application of a plant protection product to grassland with a dense vole population has no effect on that population, it's very unlikely that there will be any effect on the less numerous, later arriving population in an arable crop. Population monitoring is a very sensitive method to detect subtle effects on populations of rapid breeding mammals like common voles. Voles begin breeding early each year and have multiple large litters of young, which in turn can also begin breeding when very young. This means that we can follow the progress of 3 or 4 or more generations in a single, long field season. There are various factors that could affect voles' ability to reproduce, such as weather or habitat quality. Use of a plant protection product could also have an effect on a population's ability to reproduce. We might not detect these small effects in a single generation, but if voles breed slightly less because the grass they eat is treated, and so have average litters of only 7 instead of 8 young, and then those young only have litters of 7 instead of 8, and their young produce smaller litters, you can see that an effect too small to measure in the first generation could become quite readily detectable by the end of the breeding year, in the autumn. To vole populations by live trapping. We typically set grids of 60 to 100 traps in areas which we know to have vole populations. We set trap grids on plots which we'll treat with our test product, and on similar but untreated control plots. We know from the literature and from our own experience that voles rarely move more than 20 metres, so we can make sure we treat the whole area occupied by the trapping grid and at least a 20-metre margin around it. In this way we can be sure that the voles we trap have a worst-case exposure to the product we're testing. The traps have a simple counterweighted trapdoor. When a vole stands on the trapdoor, it gently drops through to be caught in the trap. Inside, there's food and bedding, and a roof goes on the trap to give shelter. Predators can't get you, and it's a nice place to be for a vole. We pre-bait these traps at first, setting them with a back door open so that animals can get used to them and go in and out freely. After a night of pre-baiting, we set the traps to catch in the late afternoon or evening. We return to check and clear our traps first thing the next morning. Voles are active in the daytime as well as at night, but it can get hot in traps during the daytime in summer. Trapping at night is just as effective as during the day, and more comfortable for the voles we catch. We check each trap. If it's empty, we open the back door so nothing can be trapped during the day. If it contains trapped voles, we remove them one at a time. We check them to see if they've been marked, showing that we've caught them before. We use pit tags injected under the skin on the voles' backs to mark them. If there's no pit tag, showing that it's the first time this animal has been caught, we fit one now and record its unique number. We weigh the vole
28
and record its sex and reproductive status. It's quite easy to tell males from females, and there are clear signs of reproductive activity in both. Then we let it go and leave the trap open. Then it's on to the next trap, and the next, and the next, and so on. We return in the evening to reactivate the traps, and again the following morning to check and clear the traps again. We do this for 4 nights in a row. 2 teams of 2 biologists each might typically operate 2 or 3 grids of traps in this way one week, then move on to another group of 3 or 4 grids in the next, and a third group in a third week, before returning to the first group, and so on, throughout the spring, summer and autumn, gathering data from 12 to 14 study plots. The resulting body of data, with thousands of captures, provides a wealth of information on the voles' numbers and general health through all the active parts of their breeding year. If we do this on treated sites and control sites, we can compare various parameters from the field data. We can look at body weights, sex ratio, the proportion of trapped animals that are sexually active, and the proportion of juveniles in the trapped population over time. We'd expect to see differences in these parameters if one population is doing better than another. Perhaps the single most useful parameter is the population's growth, expressed as the minimum number alive, or MNA. To calculate MNA, we take each individual vole we caught and look for the first time and the last time it was trapped. We know it must have been alive on all the days in between, even if it wasn't trapped, so it contributes to the total MNA for that site on all these days. We repeat this process for each vole we ever trapped to arrive at the MNA values. MNA accounts for voles which are present, but just happen not to be caught on some nights, and it gives the best measure of the overall population size. We can follow the changes in MNA as the population builds up from a few overwinter survivors to its peak in late summer. Any differences in reproductive rate between the test and control populations are amplified over this time. But is 6 to 7 treated plots and 6 or 7 control plots enough replication to give robust results? One way to check this is to calculate a minimum detectable difference, or MDD, for each parameter we work with. How big would the effect have to be in order for us to detect it? It's a bit like asking how many Mars bars would I have to eat before I see the difference when I stand on the bathroom scales. For most of the parameters we compare, the MDD, as a proportion of the control value, is below 50%, indicating that there is sufficient replication to detect any relevant effects on those parameters, and therefore on the common vole population. Designing and operating a long-term field study like this is a complicated undertaking and doesn't come cheap. But monitoring a population over several generations provides a very sensitive means of detecting small but real-world relevant effects on populations of small grazing mammals such as common voles.